Welcome back, everybody. So I am going to start from where I stopped in the previous lecture, just to show you how the pseudocode would look like for the bacteria ecosystem. And then we are ready to jump to the next example where we are actually going to write code and not to just be uh, thinking abstractly with pseudocode. So a pseudocode for this simple model would look more or less like this. You have a medium producing nutrient, and then you start a loop over cells. You test if the cell has no energy left. If it doesn't have energy, you kill the cell. Test if the cell type is A, so bacteria A. So if it's not full of energy, it takes up a nutrient, increments its energy, and release waste. If the cell has energy available, it grows and decreases energy. So decreases energy every time. So now we have a energy object that we didn't have before. We have this internal metabolism variable that we didn't think about before we were implementing this as pseudocode. So this is the interesting thing about building pseudocode. Then test if cell type is B. If it's not full of energy, you take up waste, increment energy. If the cell has energy, you grow the cell and decrease energy every step. If the cell is double the original size, the cell divides. And this is exactly the code I have in the CompuCell simulation that you can download from the docs, okay, the drive materials, student materials. But it's written in Python. What is the advantage of pseudocode? Pseudocode is very easy to understand and it's very easy to translate to any other language. You can implement this in any type of framework. It's not dependent on a type of programming language. Okay. And now let's officially start lecture number 3, the avascular tumor spheroid. So this is a guided exercise. I'm not going to be lecturing here as I was doing before. Before, the lectures are more like we discuss a little bit here and there, but there is very little hands-on. This is where this lecture comes into play, where you actually spend a lot of time coding and a lot of time building something. And we'll be here just to give you advice and guide you through the activity. Okay? So, um, oh, I'm so sorry. What is that? Okay. Right. So, nutrient is a diffusant that cells absorb and we have, for example, medium secreting. Cells are going to consume nutrient and grow, let's say, as a response to taking up a nutrient. If they do not take enough nutrients, they grow less. This is the kind of thing we want to set up here. Okay, it's a limiting, it's a nutrient limited growth. That's the strategy. Where do we find the implemented code? On Google Drive. Hayden, can you paste the link to Google Drive, please?
Yep, I'll go grab it.
In the of a vascular tumor spheroid, so imagine you have like cancer cells, tumor cells in a petri dish growing as you provide nutrients. We observe that it has concentric layers of cells, where the outer layer of cells grows faster and proliferates faster. There is an intermediate layer of cells that are just sitting still, not doing much, not proliferating. And then there is a core of dead cells. And we observe that this tumor grows in size. Here we can ask a series of questions. For example, how fast does it grow? How different is it between in vitro and in vivo? Why is it different? What is the relationship between the growth rate and the nutrient you provide, the concentration? Tumors absorb nutrients. We are already assuming things. I'm not observing those cells taking up or anything. I'm just observing the size of the tumor. But I'm going to assume here that the tumor is absorbing those nutrients, metabolizing, using those nutrients. And because it's absorbing nutrient, the nutrient diffuses into the tumor and decays inside the tumor, creating an exponential nutrient profile. And this is directly observable in experiment. Here, it's not nutrients that they're measuring. They're measuring oxygen pressure as a function of the distance from the surface of the tumor spheroid. So this is experimental data, and you can see very consistent exponential shape, which is beautiful. Okay. Let's remember from the last lecture that this typical diffusion length, which is, let's take this curve here as an example. Let me draw in red. If we assume this is an exponential, this guy over here is going to be your typical diffusion length, your L. And then you can do something very cool, which is you take the L that is experimentally measured, and then you can track back to your diffusion divided by gamma of your simulation. Okay? So this is answering a bunch of questions we got before. And let's make some strong assumptions here now. Let's assume that the cells are changing their states as a response to the nutrient concentration, to how much nutrients they are exposed to. If the cells have a lot of nutrient concentration, if the concentration is high, they are healthy proliferating cells. If it falls below a certain threshold, they become quiescent cells, which is a low maintenance non-proliferative state. And if it falls below an even lower threshold, the cells die, which is an irreversible process. And we have a mechanistic hypothesis here, which is that the nutrient profile and the cell response to nutrient concentration determines the geometry of this tumor spheroid and limits the growth of the tumor. There are many ways we can model the influx of nutrients. We can set constant value boundary condition. We can set a constant influx. But we can also fix the field at a constant value in the medium everywhere, which is what we are going to do. And we'll use the secretion plugin and set secrete constant concentration in medium, and it's going to do that for us. So it has come the time where you build the code yourself. When the cell dies in the middle of the tumor, does it stay as an object or gets removed from the simulation space? This is an incredible question. Incredible question. To which I am not giving an answer yet. I will let you decide what to do. Shouldn't we select death as one of the properties as well? I will recommend no, because I remember having problems with that. So I usually set it up by hand. And I recommend you do something similar. No center of mass or cell neighbor properties. I believe you have to activate the center of mass tracker, but we don't need the cell neighbor tracker. So question in the chat, what do we mean by commenting out diffusions and decays for specific cells? This is a legacy instruction for versions lower than 4.7. In 4.9, you can ignore this instruction. Do we want to select control secretion through Python? Initially, you don't need to, no. But later on, if you want to do the optional exercise, the a little bit more realistic exercise, then you might need to. But for this simple one, you don't need control secretion through Python. You can do everything via XML. So the comment about the instruction of commenting out diffusion and decay for specific cells, that's legacy instruction for versions 4.7 or lower. Is there a way to write code to automatically open and tile two graphic windows? One for cell and one for nutrient. Yes, there is. Does it take a lot of time to change the status since the nutrients move pretty slowly? To change the states of the cells. So in this basic setup, you will not see the cells changing any state because we are not conditioning any state transition to anything. So we will never see the cells changing states in this simulation. Is there anything wrong in here? This produces cells in the blob of both prolif and quiesce types. No, there is nothing wrong with your blob initializer. What could be happening is if you have another initializer below overwriting the previous. So there is a question, where should I set initial concentration? Let me resume here. In the XML, in the diffusion solver FE, this block here, there is a line that says initial concentration expression. Initial concentration expression like this. Then you come here and do 100. That's how you set it. Okay, I think people are getting to good results. I am going to do it myself now. And if you got lost, you can watch me do it step by step. All right, so CC3D project, new CC3D project. Periodic boundary conditions for X and Y, 256, and use the BlobInitializer. Then I'm going to define the cell types prolif, quiesce, and necro. And here I'm going to say contact, mitosis, and volume local flex. The next. Then I'm going to add a chemical field. So this can be neutral like this. Add. If you want me to stop, please type in the comments. Otherwise, I'll just keep it going. Okay? Fine. So here, what is it asking me to do? Secretion. Medium secretes nutrient constant concentration 100. So constant concentration medium 100. Global diffusion constant 10. Global decay constant 0.01. Initial concentration 100. Right here, 100. X and Y boundaries to periodic. Right here, periodic and periodic. Okay. Next, and finish. Now it's telling me to go to the XML and set the width to 8 and create only prolif cells. This. I'm gonna run this and see what happens. Okay. Nice. So this is what I have. It's not looking like what we expect, but it's fine. Okay. There are these couple lines here on the steppables, on mitosis steppable. So you go to your simulation steppables.py file. And there is a class called mitosis. Find that class. And then you're going to set parent child. Sorry, you are going to just delete this or comment out. To comment out this little block here, you can press Ctrl/ and it's going to automatically comment out. Or you can just delete those lines. Okay. Here in the steppables, the slide is also telling us, and we obey, to set target volume to 64 and lambda volume to 8. I just did that. And it asks us to set the volume threshold to 128. What is the volume threshold? Right here in mitosis steppables, we have if cell.volume greater than 50 cells to divide append. So it's basically adding to a list all the cells that you want to divide, but we want cells to divide when their volume is double the default, which means if our default is 64, our threshold is therefore 128. Okay. Once you have done these changes, your simulation should look like this. It's a single cell type growing and dividing. Comment in the chat, I didn't get the same nutrient field as mine is empty. Let me see how mine looks. Should be just 100 everywhere. Yeah. Yeah, so this is my situation. So if you did not get this, chances are probably your initial concentration expression is not correct. So you find your initial concentration expression in the diffusion steppables, set it to 100. And the other thing is here in secretion data, you have constant concentration, type medium, also set to that to 100. Don't see the secretions. You don't see this profile here? Did you check the other parameter values, like the diffusion constant, the decay constants? Do you have decay at cells in cell type A, cell type prolif? What do you see when you run it, Nathaniel? Nathaniel, I think your simulation is working. It's just a matter of going to configurations and unfix the maximum. So configurations, field, max, unfix. Your simulation is working though. There's nothing wrong with it. Okay, so for the next exercise, we're going to create the layers. So set up some kind of the differentiation or like change state, some kind of cell state change based on the concentration. So what we want to do is we set up thresholds, and once there is a threshold that a healthy cell crosses in terms of nutrient availability, it converts itself to a quiescent cell. And once the quiescent cell senses nutrient falling below another threshold, a lower threshold, it converts to a dead cell. So to do that, you go to the steppables, the Python steppables, and in any function step, you can get your scan of uh, cell list by type, cells of a given type, and we'll start from there. Let me just double check the original instructions to see if I have everything corrected here. To acquire these loops, you can go to CC3D Python visit and visit all cells of a given type. This is how you bring this syntax over here to your Python code, like this. And then here I can set the cell types. And I want a similar one for Quies. So I have two loops over cells by type, one for prolif, one for Quies. If you want a copy paste, the code is on the chat. Next, we are going to get our field object. You can do the same thing, like imagining you have you're working on a simulation and you want access to the syntax. You can go to chemical field manipulation, And here are all the functions you can use, all CompuCell functions you can use to manipulate a field. You can get the maximum value of the field. You can get the value of the field. You can modify a field, set field value, etc. Here we want to get the reference of the field. Or you can just type what we have in the slide. Here, though, we have to give it exactly the name of the field. In my case, it's NUTR. This the same name I have on the XML. So what I did was I went here to CC3D Python. I went to chemical field manipulation and I got the field reference. Then it gives me a line that has something random here. Then I just type the name of my field. This is case sensitive, okay? Case. And then I want to measure the concentration of the field inside these loops. So to do that, I'm going to do the same thing, CC3D Python, chemical field manipulation, and get field value. And it gives me this, value equals field 10, 10, 0. So I want it at the cell center of mass. So I'm going to use cell.xcom to get the x coordinate of the cell center of mass. Cell.ycom, cell.zcom. And I'm going to just copy and paste it below my other loop. And this is the sure. So to get that, you come here to CC3D Python, chemical field manipulation, get field value. And then I just added it to have the cell center of mass on each of these coordinates. And finally, we shall set the thresholds for concentration of the field, and the cells will change their type according to the concentration value. So for the first threshold, we have a prolif cell, so we are inside the loop over prolif cells, and we are going to set our first threshold. If the concentration is lower than 70, and you can call this variable concentration at COM, just as in the slide, but it's not necessary. So if the concentration is lower than 70, we are going to assign the cell to a different type. How do we do this? We do cell.type equals self.quiesce. Here, all uppercase letters. On the cell type, okay? And if the cell is not below this threshold, it will proliferate. So we are going to do cell dot target volume adds 0.5 to the target volume. If you have these two lines of code here for cell in self.cellList cell.target volume plus equals 1, then if we are adding here, then we want to remove these two lines, okay? So I'm going to remove them. And the growth, I do the growth inside the for loop. So this is a very minimalistic way of implementing this type conversion. Now let's set the concentration thresholds for quiesce. So we are going to first, there will be a threshold for quiesce going back to proliferation. A quiescent cell can reversibly transform into a proliferating cell if it gets access to nutrient again. So to do that, we are going to test if concentration is greater than a threshold. We are going to do cell.type and we assign self.prolif. Now let's set the threshold for the cell dying, the quiescent cell dying. If the value is below something like 40, and these threshold parameters are arbitrary, okay? They are not literature informed of anything. This is just demonstration. So if the concentration crosses the lower threshold, we are going to assign a necro cell type to this cell. And you can either let the cell be, so it will just exist and hang around, or you can do target volume equals 0. If you do that, the cell will shrink and it will be a very cool visual output, although not biologically realistic. There are other ways you can set the cells to die. This is one of them, just by making them disappear. Sorry. So now if I run the simulation, yeah, these are the quiescent cells emerging. And they're crossing the threshold. And eventually, when the nutrient crosses the 40 threshold, the cells will start to become necro cells and die. Okay, now the cells are becoming necrotic and they are shrinking. So question in the chat. An indent does not match any outer indentation level. This usually happens if, for example, inside a class, you have something like this, or if inside a function you have something like this or something like this. It has to match exactly the indentation of your if you share a screenshot, we can help you. Oh, okay, that's it. Also
Those,
in the for loop.
sorry, quick note, those vertical lines in Twedit will help you find where your indentation is correct.
Mhm.
You can see within the for loop, there's a vertical line that drops down to the next for loop. If that line is broken, it usually means that something is indented incorrectly. Anyway, that's all.
Yeah, and I think this instruction over here, comment out diffusions and decays for specific cells, I think we have to do that because that's not quite the behavior I was expecting. So let's you select all these lines here in the XML for diffusion and decay coefficients on a per cell basis. And then you are going to hit Control/ or Command/ to comment them out like this. So we are basically removing them from the simulation and just the global settings are going to play. So after doing that and rerunning, the simulation even runs faster. Yeah. The simulation runs faster when we don't set a diffusion or a decay on a per cell basis, which is awkward. It should be the same amount of computation, roughly. Yeah, so after commenting out those portions of code, I'm getting what I was expecting, which is this irregular shaped cell organism growing, and there is a necrotic core in the center that shrinks and causes this cell structure to deform. And it grows only at the boundaries. So only the cells that are in direct contact with the nutrient are the ones allowed to grow. So we can have these very asymmetric, not this one is symmetric, but very irregular, um, irregular kind of organism. Eventually, it's going to fill out the entire space and the cells will die. So which lines to comment? Let me come back to my to edit. In the Twedit, you are going to find your diffusion solver FE stepable. Inside the diffusion solver FE, you have your diffusion data section over here that has global diffusion constant, global decay, and initial expression. Those three are the only ones that will be active. All the other ones you can comment out or delete. If you want to comment them out, you select them and you hit Control/, does comment and comment, and Command/ on the Mac, and comment and comment command. Okay? You can either leave them commented out or you can delete them. Usually we like to comment them out because if we want to change something, we have the code here, we don't have to get it elsewhere. Then if you do that, you should see something like that. Oh, I stopped the simulation. The other thing that is better to have here is to, I think yeah, fixing the minimum value of the field. That's much more informative because now if it's blue, I know it's 0 in the center. So and fixing the lower. Can you please show the parts you just commented out one more time? Yeah, of course. I can show them 10 more times. Right here in your XML, you have your diffusion solver FE. Inside this block called diffusion data, you have your nutrient name, nutr, your diffusion constant global, your decay constant global, and your initial concentration expression. These lines are the only ones active to get the simulation to work the same as mine. The other lines, namely diffusion coefficient for cell type prolif, decay coefficient for cell type prolif, diffusion coefficient for cell type quiesce, decay coefficient for cell type quiesce, diffusion coefficient for cell type necro, and decay coefficient for cell type necro. These lines you are going to comment out. How are you going to comment them out? Select them and hit Control slash or Command slash if you are on Mac. You have to be careful to not comment out anything else. If you comment out together this line that says diffusion data over here, you'll get a bug. Your simulation will crash. If you comment out the other line, the initial concentration expression in your cells will die instantly. If you forget to comment one of the lines, your simulation will not behave as expected. So select the 6 lines we want to comment out and hit Control slash or Command slash. Can you show the line where the volume of necro is being decreased? Yeah. So here in new simulation steppables.py, I have the lower threshold condition. If the concentration is lower than 40, I set the target volume of the cell to 0. This is basically making the cells shrink, but you could argue that's not biologically realistic, and then you can try commenting it out and see how the shape changes. That's one of the first tests. Can you reduce it over time? Yeah. Or you can simply not reduce it. Let's see what happens if we don't reduce it. First, what do you expect to happen if we don't set or reduce the target volume of the necro cells? Romasa, what do you expect? So that the tumor will basically grow as a sphere, right? Necro's taking up all the space and growing in size. Necro shouldn't be growing in size though. Necro should be just preserve its size. So see, in my simulation here, the necro cells, they are not growing or shrinking. They are just staying there. They're just sitting still. This is more similar to the image, the biological observation we had in the beginning of the lecture. Oh, I see. Yeah, that's correct then. So I'm taking a look here at the code sent by Maisha. Secretion data. Yeah, your global decay constant is too low, and that should do. One of the challenges of this exercise is to have the necrotic cells shrink at the same time as you keep the spheroid a spheroid. So in CompuCell, you can generate your own field color and your own color bar for certain cell states. Let's say you have a cell and your cell is consuming nutrients, and you want to see as a color display how much nutrient the cell has inside it, which is some arbitrary variable that you have in Python. You can use this variable to set a color field. And we do that using tracking fields. Tracking fields are easy to set up using Twedit. You go to Python, and then you go to CC3D Python, and then you go to extra fields. Now there are a bunch of options here. You can set a scalar field and a vector field. We don't have tensor fields because they are not easy to visualize. But we have scalar fields, so for example, the concentration of something inside the cell or the state of the cell. And we also have vector fields. For example, if you have cell polarity or something like that. And then there are functions. The create function goes in the init function of your steppables. The clear and the write functions, they go in the step. Those are used to reset and rewrite the values of your tracking field. And then using that, you can see the state of your cells or the concentration of things in your cells from player. And as a homework exercise, final exercise, if you're interested, you can do nutrient-based growth. In this exercise we did today, this guided exercise for the tumor spheroid, we are using cell type conversion, and the criteria for the cell type conversion is simply a concentration threshold. However, something more biologically realistic is to have the cells uptake the nutrients, and then you track the amount of nutrients taken up by prolif cells, which you can print in player using tracking fields. And then based on the amount of nutrients they have, they decide whether they grow, whether they become quiescent, or whether they die. So this is homework exercise. If you are interested in implementing this, this is very similar to the idea behind the bacteria proliferation, the bacteria simulation, where you have to track the amount of content in a cell before you decide what to do with it. What is the advantage of having this? One advantage is that you can model metabolism. And the other advantage is if your cell loses access to nutrient, it doesn't instantly die. There is a time period where it's consuming the nutrient it got in the past, which is more realistic biologically. If you want to know more about cancer, and if you're interested in developing a more realistic avascular tumor simulation in the hackathon. This is a good paper suggestion to introduce yourself to tumor and cancer. And you can start here by implementing nutrient-based growth. And we do have a demand for vascularized tumor, which is something like it's a simulation we had before and we lost. It exists. There is a beautiful video of it. I think James showed it in one of the earlier lectures. So if you're interested in modeling vasculature besides tumor, the influencing the growth rate of the tumor, we do have a demand for that, and we will support you for your hackathon project if you choose to do that.
A year or two ago, there was a paper that published that rebuilt that simulation and explored it more. It's in the CompuCell publications website.
And you can also download this simulation from the drive folder. Okay.
So there was a question about gastrulation and whether gastrulation results from the death of cells in the center of a solid aggregate. And in general, in most species, that's not how gastrulation happens. Gastrulation happens because of polarization and the formation of a lumen by active pumping. There can be some small amount of cell death in some species in gastrulation, but in general, the lumen formation in the blastula happens when the number of cells is small enough that you don't have significant cell death. But it's an interesting question about why one mechanism rather than the other might be the one that is more common biologically.
In the nutrient example, what exactly is this line doing? TOT underscore amount equals secretor dot uptake inside cell total count. Cell 202 total amount. So this line is 1. Making the cells take up material from the field. Second, the uptake inside cell total count counts how much the cell has taken up. Dot tot amount takes this value and assigns it to the variable tot underscore amount. Now, so you are doing two things. You are uptaking, and second, you are storing in a variable the amount taken up. Another question, what are the roles of the 2 and the O2? Yes, these are parameters for the uptake. The one on the left, the 2.0, this is the maximum uptake. This is the maximum amount of field material the cell can take up per pixel per Monte Carlo step. The 0.2 is the fractional uptake. Is how much in percentage, or not in percentage, how much in terms of fraction of the field the cell consumes per pixel and per unit of time. So 0.2 means 20% of the current content in the field the cell will take up per pixel per unit of time. Avascular tumor. Let me see if I have this demo working. My nutrient-based model very quickly runs out of nutrient and every cell dies. Is this expected behavior? Depends on your parameters. If your parameters are exaggerated in one direction, yes, this is expected behavior. If they are the same as my parameters, no, this is not the expected behavior. This is the nutrient-based growth, tumor growth simulation. So for example, let me open here. Initial concentrate, global decay 0, global diffusion 10, initial concentration 100, constant concentration 100, periodic. And in the steppables, I have the total taken amount, total amount, blah, blah, blah. So I think it might be just a matter of removing the decay here. Set the decay to 0. Because you already have uptake. If you already have uptake, you don't need global decay. So think of this 0.01 as it is 1% of the field in every pixel of the cell per Monte Carlo step. Which means if you have field 100 and your cell is size 64, no, it's going to take 64 units of the field per Monte Carlo step. Wait a second. No, 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 no. It is 1% per pixel, so it's 6.4. Sorry, no, 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 it's 1 times 64. 64. Yeah. It's taking 64 units of the field per Monte Carlo step, one single cell. This is what the 0.01 decay is doing. So of course it's going to change everything. It's a huge uh it's a huge impact. 0.01, it's a huge decay.
Well, think of it this way. 0.01 means that after 100 Monte Carlo steps, you've lost 2/3 of your chemical. That's very fast decay, usually.
Yeah. Yeah, that's a better way to think about it. Here you can ask all sorts of questions. For example, the proliferating cells, we expect them to consume more nutrients. So these parameters might be different between prolif cells and quiescent cells, right? So there are a lot of things you can do here in terms of assumptions and mechanisms. It's essentially the same behavior as before, right? Because the cells are still doing the same thing. So the sensitivity of the simulation to changing the way the cells absorb nutrient and store energy doesn't change much. But you could have situations where they do behave extremely differently. Let's say, for example, you simulate a situation where you stop giving nutrients to the cells. Okay? A nutrient deprivation perturbation. If you have your nutrient-based growth, your cells are storing nutrient and tracking this amount and using that as a reference. So they might survive in a nutrient deprivation perturbation. While in the other case where they just decrease the nutrient and change their state based on the current concentration, once you apply the nutrient deprivation, they will die instantly. And there we have it. This is, well, it's looking to me like a self-limited system. It can't grow to confluence. And if it does, it's going to die because nutrient is provided by medium. So it's a self-limiting system. It heavily depends on how you set the boundary conditions. And there is a very cool demonstration using boundary conditions that you can have your tumor moving towards the boundary condition that provides nutrient, even though you didn't set any cell migration mechanism. So you can derive this kind of whole tumor movement without migration just by having one boundary secrete nutrient. So there is a gradient of nutrient, and the tumor will grow more on the side closer to the nutrient source, and it will get closer and closer to this nutrient source. So there are all sorts of kind of things you can explore with this simulation. And I think that's it for today. And I thank you so much for sticking around. I hope you had fun. So Barger, feel free to screen share and we can take a look at your problem. Oh, there is an indentation problem in line 32. It has to be one to the right of else, line 32. You have one extra indentation there. Let's save and try again. Could we use cell parameters to define a field as the simulation evolves? I'm thinking of osmotic pressure on a cell membrane as a function of the cell volume. Rate of nutrient consumption as the concentration of species vary in the area. Cell parameters define a field as the simulation evolves. Yeah, I think that's a trivial yes, if I understood the question. Yes, of course, like the behavior of the cell can definitely change the field. Yeah, the field values, yes. And you can also build a field from those behaviors. Okay, so it didn't work. Let's see. What is that you see when you run? What happens? Ah, okay. What happens when you run it? Do you get an error message? Okay, so it is running. Oh, you do not have oh, you do have cells. They are there. Okay. Can you go to visualization and check cell borders? Okay, so we have the cells there. So the simulation is working. Can you hit stop and play again? Okay. Please show me your XML file. Scroll down. Show me the field settings. Set global decay constant to 0.01, so just add a 1 there. And save. Now let's run again. Can you show me the field? The field visualization, okay. Ah. 10 to the power of 3. Okay, let's go back to the XML. Mm-hmm. Show me your steppables again. Might be there the problem. Ah, I know what it is. Go to XML. Go to the XML. I know what it is. This is the secretion line I'm going to paste in the chat. You are going to copy this line and paste in place of your line 66. Line 66 says secretion type medium 100. You are going to replace it with constant concentration. Save and run. Yeah, there we go. That fixes. I think now we're getting the expected behavior.
Pedro, we've got Raghu sharing his screen
Yeah.
now. He's having issues with his cells not proliferating.
Yeah,
Okay.
so
With,
due to
oh, yeah,
proliferation,
Raghu.
I'm not getting the the other cells. I'm only getting the proliferating cells, and
Mm-hmm.
it might just be processing power on my end.
Let's see what the simulation does.
It stays around like this size the entire time and doesn't make any new cells.
I'm looking at your Twedit right now.
Oh.
Uh-huh. So you're getting an error, and the error
Yeah.
goes like, please define secretion plugin before you
Yeah,
do
I don't know why it
anything.
just keeps crashing now. It was working before.
Yeah, so you have to initialize the secretion plugin in the XML. So go to your XML.
Wait, I was trying to do the nutrition example,
Yeah.
so maybe it's just not running because I had the error for the nutrition one. I didn't save over when I got rid of it. Yeah, so if you
Yeah. So in the XML, you have to load the secretion plugin.
see, this is working though. This is running right now.
And what's the difference between this and the other one?
The this version is without the nutrition. This is
Oh
just I'm
yeah.
just trying to get the cell proliferation.
Yeah, that's exactly what I'm saying. When you do secretion in Python, you have to initialize the secretion plugin in XML. So go to the version with the nutrient thing.
Oh,
Now
I
place your
removed it.
cursor anywhere outside the block.
Mm-hmm.
Now go to CC3D which is a menu up there somewhere.
Yeah.
And then you're going to find plugins and then secretion plugin. Right. Now I want you to delete everything inside the secretion plugin.
Everything side of it.
Everything inside, yes. Delete, yeah. Now save and run. Are you getting another error?
Yeah, no error, but it's still not like the proliferation's not what it should be, like the example you were showing earlier.
Yeah, but at least we don't have that bug anymore. Okay, let's
Yeah.
take a look at your XML again. Scroll down. So in first thing in secretion type medium, I want you to copy and paste the other secretion type I have on the chat, constant concentration medium 100. the one I have on the chat.
Let me see if I can find the chat again. So I'm replacing the one with the 100 out.
Yeah,
Just
replace
replace
the whole line.
Okay. And then I'll run that and see if it makes a difference. So I replaced it and it's running again, but no errors. But this, I still don't get the quasi cells. I'm only getting the proliferation cells.
Okay, yeah, let's keep taking a look. So this is correct. Let's go to the steppables now. Yeah, so here you don't have the nutrient consumption yet.
Yeah, I removed it because I
Ah.
wasn't getting this first step to work. So when we went back to when I shared my screen, I removed it
Okay,
to
so let's add it in now. Add it in.
yeah.
Create
I have to
scalar field.
copy it from here.
I can copy and paste the
I think I
whole
got
thing. Oh, do you have it?
Yeah, most of it at least. If I just get rid of all this and just paste that there, that should be everything that needs to be in it. I believe, except for, yeah, the quasi's there too. Does it look all correct? Formatting wise.
It looks okay. You can try 7.1.
1 second. I'm gonna move this bar to save it. High controls. Doubles. The bar shows 0. The nutrient take-up bar is just completely zeroed out as well.
Can you show me the simulation running? I'm seeing
Yeah.
your Twedit.
And then if I change it to, of course, if I change this, it's just the proliferation cells again.
Go back to the diffuser field.
Or diffuse field.
Uh-huh.
You mean the nutrition
Yeah,
one?
yeah.
Or
Yeah. Okay. So it is there. It is 100
yeah.
and it is decaying. Okay, let's the simulation run. Can you show me your XML?
Yeah.
Okay, show me your steppables. Zero 0.2. Show me the simulation again, the player window.
I still have it running. So this is 200, 100, 320 iterations in so far, and it still looks just like red.
Oh, so actually, probably the problem is that it's extremely slow.
Yeah, that's why I was thinking maybe this is a computational problem with my computer. Because it's going like every like maybe 10 seconds it goes up an iteration. Like
Oh,
up to
this is way
390.
too slow. There is something is off. Something is really off.
Yeah,
You
because
should
I've
How
never
remove
had
often are you
this.
updating the screen? What's the interval between updates? Every
it's
10 Monte
10.
Carlo steps?
Yeah, every 10.
Huh. Well, so one thing here is you're saturated for the field, so you have to float the field. So you have a fixed top value for the field, you need to float it.
Okay.
No, wait a sec. Actually, hold on a second. Min is 91.
Yeah.
So it looks like the field is just constant. It's not changing.
It
Why
is
is
changing, but it's extremely slow.
no, but this shouldn't be. Something is wrong. There's something. can we look at the other field, what else do you have besides nutrient?
Oh, nutrient. I have nutrient uptake, and that's also
Okay, that's a tracking field,
yeah,
and that's 0, so it
yeah.
shouldn't be 0. So something is wrong. The nutrient field is not doing what you think it is.
Can we let's try to remove the tracking fields, but it's so weird. Like, it shouldn't matter.
Yeah, because I think
So
everything else
complicated.
worked up to the point where I was doing the proliferation if it was at a certain size to go to until there it was working, and then
And running fast?
yeah, it was work up to this today's like until I did this, everything would run at the same speed that you were doing it at. But until I
Uh,
got this exercise, everything was running slower now.
huh. Um,
Why are you doing this take up clear? Why are you doing a clear in line 26?
to
Because it's
redraw the field because the cells move and then you'll have to reset everything and draw everything again for the tracking fields.
No, the tracking field self-draws. You don't need to do that. That'll slow you
Hmm.
down a lot.
Yeah, I'll try to remove every tracking field you have, but you can try removing this one first.
But you never need to do that.
I'll run this and see if it makes that big of a difference.
And still always returning 0. Shouldn't be
Yeah.
good. And the nutrient value is non-zero. So the amount being taken up is where are you doing the uptake of the field?
Down here.
Okay, let's see. So 4 cell and cell fed cell this values field. Hold on a sec.
Oh, wait a second.
Am I doubling? Is there two of
You
them?
have a double step function, yes.
Yeah, I have
So
no
if I get rid
idea
of,
that.
if I get
And
rid of this one, it should work, right?
Well,
yeah,
I
just
don't
get rid
know,
of it.
but having 2
J
of them is not a valid
Scroll up a
tripod.
little bit. Scroll up a little bit. Step. Okay, let's try again. Well, that justifies the slowdown, at least, having functions. Iterating over everything twice. Um, can you
Well,
show the cell field?
at least you're having a take up now. See, now you're getting chemical taken up
Yeah,
by the cells.
yeah.
Yeah.
Can you zoom in?
So
Yeah.
now the diffusion constant is very low in this field. Not sure why it's so low, but anyway.
This is the tracking field, James. This is not the
No,
neutral
but
field.
you, okay, sorry. Can we see the regular field?
Cell field or the nutrient?
Nutrient.
It has to grow large enough to do anything.
I
Yeah.
don't understand why it's not showing that.
And why is it so low?
7. Auto scale it. Put the field on auto scale. So go to the preferences and select auto scale.
Preferences, field, right?
Right.
And then,
You'll have to auto scale the
Unfix the field min and max. Yeah, and hit OK. Zoom in again.
yeah, so that's slow, but it's doing what you expect.
Yeah.
yeah.
Now, show me your steppables again from start to end, because I think there is something messing up everything.
You may also be putting, one thing that could be happening is you could be doing a get field or something like that inside of a loop. That slows
Mhm.
things down a lot.
Okay. So this
Scroll
is
down.
the top of my steppables.
Yeah, scroll down. Oh, it's looking fine. I also have the field references and secretor references inside the step, and it's, yeah, it does slow down a little bit, but go back up to your main step function. Yeah, this is just basically a copy and paste of my code.
Yeah, I took a screenshot of when you were showing it, and I just pasted it in to see if it
Yeah.
would work any faster or if I was making any mistakes. And
Show me your XML again. There must be something weird. Show me your diffusion steppables. Diffusion over FE, okay. Global decay, saturation. Scroll up.
are my dimensions too big for this, maybe?
Oh, wait a second. Scroll down. Oh no, but this is a voxel conversion. No, doesn't matter. No, that's the same dimension I set mine. Neighbor orders one there, two there. I can't find anything that is actually slowing down or something. Is the other one working fine without the nutrient-based growth? Does it run
Yeah.
fast and fine?
Yeah, everything else runs fast and fine, except for when I got to adding the differentiation at cells, at sizes, from then onwards, it's been slower.
I can't see a reason.
Because I've been, like I said before class, I was running a lung cell model on my computer before class, and that runs perfectly fine. And it has way more variables
Yeah,
than this does,
yeah.
and it runs faster.
Which your version is 4.9.
Yeah.
I was just going to say, I wonder if there's something trying to optimize with the GPU, but if there's no GPU,
Mm,
but if 4.9, I don't think does that with the solvers.
no.
That's a 4.10 feature.
Yeah.
On projects open. If I open your version, like just your actual
Now, why
code,
don't we run the version, the one without that extra field in it?
Or the one you download from the drive folder.
yes,
I'm
I'm
sure it's exactly the same.
this one's a 3D model. That's fine.
So you are running a 3D simulation.
No, this is the one from the
Okay,
folder.
okay. Yeah.
This one runs slower, obviously, because it's a 3D, but let me get
Yeah.
1D version.
Did you try the one from the drive folder?
Yeah, this is the one from the drive folder. This is the tumor one
Can you put
from
it
the drive.
in 3D? It's a 3D simulation. What? Go to your XML.
This is your version, but if I went to
This
mine,
is my version.
my point, yeah, this is your
Yeah,
version. My
scroll.
point was that your version goes faster on my computer than my version
Wait,
goes on a
but why
computer.
is z equals 5? Set z equal 1. And yeah, z equals 1. Save and run. I don't know why z was 5 there. I have no clue. Here on my computer, the simulation that I uploaded to the drive folder has z
Yeah,
equals 1.
if I have z equals 1, it says that the
Yeah.
boundary conditions for it is incorrect. It needs to be
Yeah,
greater
yeah.
than 1.
Go back to XML. Remove z boundary condition in there. Remove this line. Go all the way down. And yeah, that's it. Save and run. And I was like so suspicious because that was a funny looking simulation. It wasn't looking like the
Yeah,
a
this one goes
2D
way
simulation.
quicker.
Okay,
I was so confused why it was going
let it
so
run. Let it run and let's see. And let's visualize the cell field.
Yeah, that makes
Yeah.
more sense.
Now
As
that five didn't come from my simulation, okay?
I don't know where it came from because I just left it I didn't touch any of that stuff. But yeah, okay, that works. Thank you.
All
It was so
right, yeah.
confusing.